Hello and welcome to m252 Calculus 2 here at Cañada College. My name is Lapuz. In this video we'll be doing checkpoint 3.20 from section 3.4, and that is the partial fraction decomposition. In this problem they want us to set up the partial fraction decomposition for this integral, and they told us not to solve for it, and it looks like it would be a little too messy to solve for, so we won't solve for it. We'll just do the partial fraction decomposition. And to do that, we want to make sure, first thing to check is to make sure that the degree of the polynomial in the numerator has a degree that's going to be less than the polynomial in the denominator. And so looking at the polynomial in the denominator, we have x squared squared, so that's x to the fourth, and another x squared, another x, so that's x to the fourth, x to the sixth, x to the seventh, so this is going to be clearly a degree higher than 2, and so we're good to go through the partial fraction decomposition. And that will, let me see, let's rewrite the original fraction, that's x squared plus 3x plus 1, divide the whole thing by x plus 2, and x minus 3 quantity squared, and then x squared plus 4 quantity squared. Alright, now if we take this piece by piece, we'll take a look at this first factor. By the way, everything's factored in the denominator. That's great because we don't have to do it ourselves. And now that everything's factored in the denominator, we'll take it factor by factor and create the terms that we need to create for the decomposition. So I have a linear term for the first factor, x plus 2, and the algorithm tells us that we're going to want a degree less in the numerator. So if we have a linear term in the denominator, the degree less in the numerator, it'll be constant. All right. Next, we have a factor that is being squared. And so whenever we have a factor that has multiplicity bigger than 1, we want to create a duplicate growing multiplicity. So this will actually require two terms. A term that would have an x minus 3 and a term that would have an x minus 3 quantity squared. All right, and so that's how the decomposition will work. If we combine this, we get this fraction. If we combine the left-hand side or the right-hand side into one fraction, we want to allow for these two terms to be able to identify that, hey, there's an x minus 3 term there. All right. Now, clearly, the term that would go above the x plus 3 is going to be a constant term. And what we have to do is that also identify that this x minus 3 quantity squared is actually a linear term with multiplicity 2. So because it's a linear term, this is also going to be constant. So these two are linear terms, terms, and then this one just has a multiplicity of 2. Okay, or I would say linear, not terms, but linear factors. Okay, so that takes care of that second one. Now this last one, we have to note that this is, okay, so this is linear, multiplicity 2, and then this one is a quadratic, and just to be more precise, this is an irreducible quadratic. Not only that, but it also has multiplicity 2. So the power tells us that there's a multiplicity 2. So the fact that there's multiplicity 2 means that we're going to have to create 2 more fractions. And the first fraction will be just the irreducible quadratic itself. and then the second fraction would be the irreducible quadratic with the power. Okay, and if this was to the third power, you'd create another term. All right, now the numerator for an irreducible quadratic for these two terms will be a linear term, because this is a second power, and so the most general linear term would be something x plus another constant. So C, we're in the letter D, x plus e. And this is also a quadratic with multiplicity 2, so the numerator would be linear yet again. So the next linear term would be fx plus g. And we don't consider this as a fourth degree factor, because this is a quadratic that has multiplicity 2. So this is quadratic multiplicity 2. So because it's a quadratic, the numerator remains linear. All right, so I think that's it. This is our decomposition setup, and to solve for this, you would have to solve for 5, 6, 7 unknown constants, which would be a little bit of a task. And then once you do that, you would break this up into 5 integrals that you would integrate. And looking at these, the last 2 integrals, you'll probably need to break those up as well, or do some sort of substitution to make it work. But in any case, you have a lot of work to do if you were to solve for this completely. So they just asked us to set it up, so it's all set up. All right, good luck.